Right, I wanted to do a brief little review of some of the topics from Chapter 3. Um, chapter 3 goes along with Chapter 1, um, so that's why I'm kind of doing them back to back. And then when we start talking more about probability, that's when I'll tie in Chapter 2. So I'm going to kind of review by topic, sort of. So Chapter 3 was dealing with bivariate data. Um, what we talked about already in Chapter 1 was univariate data, where you have one variable, and if you were told to describe, you used the acronym CUS. Well, now, if we're looking at bivariate data, two variables, the acronym that you would use is FUDS. So you would talk about the form, you would talk about if it's linear or if it's curved, um, just what the general kind of shape of it looks like. And then you would talk about any unusual points. Those might be outliers, they might be influential points. And there's a difference between those two. We'll talk about that eventually. Direction, you're going to tell if it's positive or negative. And then you're going to also talk about the strength. So you're going to say like really strong or fairly strong, moderately strong, weak, fairly weak, really weak, moderately weak, something like that. Okay, here is your general formula for when you write an equation of a least squares regression line. Make sure that you put the hat on the y. When you see this y hat, that is the predicted y value. It's not the actual observed y value, it's what the line is predicting the y value to be. A is the y-intercept. That's what y is predicted to be when the x value is 0. B is the slope. Remember, you can take any number, put it over 1. Also remember, when we talk about slope, y stuff is on top, x stuff is on the bottom. And here we're talking about y hat. So for every increase in 1x, your predicted y is going to increase or decrease by whatever b is. Okay, I just wanted to show you a picture of a scatter plot and what an equation would look like. When you want to get the equation on your calculator, you can do it several different ways. Here's information about how to get your information in the table. So you would get your a value and your b value, so you'd be able to write your equation. Remember, it's y hat equals a plus bx. You would just fill those in. But you also get your r squared and your r. R is correlation. You can also do that in a blank page, but this time it's menu 614. But again, you get your a and your b for your equation, r squared and r. So you get the same information. Let me show you, this is different data, but it'll work. So if I type my data in, I could go to my blank page, I could do menu 614, the a plus bx. I have to say what my x list is, which was homework, and my y list would be test, and I hit OK. There it is, all my information. But I could also graph it. So if I go to my pink graph and I put homework on the x-axis and I put test on the y-axis, I could do a linear regression. Now this doesn't look very linear, but maybe it's because of the scale that the graph put it in, so maybe if you tried getting it closer to starting at 0, like that. That looks a little bit better than it did before. But anyway, I could do a linear regression. I could do menu, analyze, regression. and then show linear a plus bx, and then I can get my equation here as well. And that might not be a bad way to do it, because now I could make a residual plot. Once I've done a regression line, I can turn it into a residual plot. I'll come back to that in a second. The only reason that doing it this way might be better is because you get your r squared and your r value that way, whereas on the graph, you're not given r or r squared. Okay, correlation. Some things to know about correlation. That's r. R is always going to be between -1 and 1. The closer it is to -1 or 1, the closer it is to a line. So like this is pretty close to -1, and that's a really good thing. It's a very strong correlation, just in the negative direction. But the closer that r is to 0, the points are more scattered. So like here's an example of where your correlation is 0. It's really almost impossible to even find a pattern. And then also r has no units. Okay. You are going to need to interpret, I think, a lot of stuff on the AP exam. So in my previous notes that I made, I said you should probably start a page of notes for interpretations. And off the top of my head, I can't remember what we interpreted on the last video. Oh, it'll come to me, but we did one of them already. And then you're going to need to interpret r, and you're going to need to be able to interpret r squared. You're going to need to be able to interpret slope and y-intercept, and we will add to this list. But anyway, here's your interpretations. Make sure when you're talking about correlation, you talk about both the strength and the direction. So positive or negative, and then how strong it is. R squared, the interpretation is right here. I would recommend just writing that out and following it. This one kind of confuses people, but it's the percent variation in whatever the y variable is. So if I was doing my data that I had on the calculator, so my y variable was test scores. So the r squared value was 0.0807. Okay, so that would be, if I move the decimal place, that would be 8.07%. So 8.07% of the variation in the test scores is explained by this least squares regression line. That's how I would interpret r squared. Okay, residuals. Here's your formula. A residual is your observed minus your predicted. Observed is y, predicted is y hat. The predicted are on the line. That's what your line is doing, making predictions. The actual observed values might be above the line or below the line. If what you actually observe is above the line, that means you're going to have a positive residual. That difference will be positive. So that means that we under-predicted. If we have an actual observed value below the line, that means that this difference is negative. So what we predicted was too high. We over-predicted. So write that residual formula down somewhere so that you don't accidentally get these mixed up. How to make a residual plot, I'll go back to my calculator. At this point, after you've done a linear regression, all you have to do is change the y-axis to stat.resid, and there's your residual plot. But you have to do the linear regression first. Okay, so I have that written right here. Always do the linear regression before making a residual plot. So a residual plot tells us whether or not a linear model is appropriate. You want it to look all scattered like this. That's a good thing. That tells us a linear model is appropriate. And your calculator, when you do a regression, a linear regression, it's going to calculate all the residuals and kind of store them. So the next time you graph data, if you forget to do a linear regression and you hop right to a residual plot, it's going to use old residuals from a different problem. So always do the linear regression before making the residual plot. So again, here's what we want. We want scattered. That tells us that a linear model is appropriate. That does not necessarily mean it's a good fit. It just means a line is better than a curve. I'm going to write that down. Not necessarily. Not necessarily a good fit. It just means a line would be better than a curve. And a curve could mean exponential or power or quadratic or logarithmic or something like that. If you see a curve in your residuals, that's no good. Okay, so a linear model would not be appropriate for that data. Also, if you see in your residual plot, okay, if your dots look kind of like this, where you've got this like fanning out effect, that's also not a good thing. A linear model would not be appropriate. Okay, so that's where I wanted to stop for today, just to kind of talk about basic stuff. Residuals, you might have to calculate residuals. And the way that you would figure out a predicted value would be to plug in a value for x. You could get your predicted y value and compare it to an actual y value, and that's how you would get a residual. Okay, that's all for today.